Introduction. In an increasingly resource-driven world, the journey from simple raw materials to high-value end products underpins the modern economy. From molecules to millions takes you behind the scenes of the key chemical and process engineering industries, agrochemicals, petrochemicals, petroleum and natural gas, cement, and food processing, to reveal how basic feedstocks are transformed through physical and chemical operations into the goods we rely on every day. Along the way, we'll unpack detailed process flow diagrams, examine capital requirements and revenue streams, and show you how smart investment can turn those molecular building blocks into real financial growth. Objective 1. Classify the major organic and inorganic raw materials and understand their unique roles across industries. 2. Map the core unit operations: crushing, blending, distillation, reforming, crystallization, and more, using clear 16:9 process flow diagrams. 3. Quantify the financial scope of each sector by assessing typical CAPEX, annual revenue, and return on investment for a medium-scale facility. 4. Compare investment performance across industries to identify the most attractive opportunities. 5. Recommend targeted investment strategies and outline future trends in sustainable feedstocks and green process technologies. By the end of this video, you'll have a holistic understanding of both the chemistry and the economics that turn raw molecules into multi-million-dollar ventures, and the insights you need to make informed investment decisions in these critical sectors. Expected core areas that are covered in this study are as shown in the outline below. 1.0 Raw Material Classification. 2.0 Agrochemicals Industries. 3.0 Petrochemicals Industries. 4.0 Cement Industry. 5.0 Food Industries. 6.0 Petroleum and Natural Gas Industries. 7.0 Evaluation CAPEX, Revenue and Return on Investment of Industries. 8.0 Investment Strategies. 9.0 Conclusion and Future Outlook. 1.0 Raw Materials Classification. Raw materials are also known as feedstocks. Raw materials are the fundamental substances, natural or synthetic, that are introduced into a process to undergo chemical transformation. Raw materials could be classified into the following two classes. 1. Classification by source of raw material. The two sources of raw materials are natural sources and synthetic sources. These imply that the materials are available freely in the environment's naturally sourced raw material. Raw materials that are synthetic sourced are produced by human. 2. Classification based on the origin of the materials. According to the origin of feedstocks, we have two classes of raw materials: organic and inorganic raw materials. Organic raw materials are carbon-based compounds such as hydrocarbons, crude oil, natural gas, carbohydrates, sugars, starches, oils/fats, and biomass, polymers. Inorganic raw materials are mineral ores, example, limestone, bauxite, etc., salts, example, sodium chloride, potassium, etc., acids/bases, example, hydrogen tetraoxosulfate, 4, sodium hydroxide, etc., and metals, example, iron, aluminium, etc. 2.0 Agrochemicals Industries. Agrochemicals are the chemical products used in modern agriculture to enhance crop production, protect plants from pests and diseases, and manage soil fertility. Key categories of agrochemicals include 1. Fertilizers. These are grouped into the following. A. Macronutrient fertilizers. These supply primary nutrients like nitrogen, phosphorus, potassium. Examples are urea, ammonium nitrate, superphosphate, potassium chloride. B. Secondary and micronutrient fertilizers provide calcium, magnesium, sulfur, and trace elements like iron, zinc, copper, manganese, molybdenum, essential for plant metabolism. 2. Pesticides. These are grouped into the following. A. Insecticides. Control insect pests, e.g. organophosphates, pyrethroids, neonicotinoids. B. Herbicides. Suppress or kill weeds, example, glyphosate, atrazine, 2,4-D. C. Fungicides. Prevent or treat fungal diseases, example, azoles, strobilurins, copper compounds. D. Nematicides and rodenticides. Target nematodes in soil and rodent pests. 3. Soil conditioners and amendments. These include A. Lime, CaCO3, and gypsum, CaSO4, to adjust pH and improve soil structure. B. Organic amendments. Compost, biochar, manure to boost microbial activity and water retention. 4. Plant growth regulators. These hormone-based chemicals that modify physiological processes, auxins, rooting, gibberellins, stem elongation, cytokinins, cell division, ethylene inhibitors. This section will be focused on the process of producing fertilizers. 2.1 Production of fertilizers. Production of fertilizers starts with the production of ammonia. In this study, we will consider the production of ammonia via the Haber-Bosch method. The process flow diagram here illustrates the production of ammonia via the Haber-Bosch method. Here's a concise breakdown of the key steps involved in the Haber-Bosch process for production of ammonia. Step 1. Feedstock preparation. Methane, CH4, and water, H2O, are the primary feedstocks for ammonia production. Methane is often derived from natural gas. Step 2. Water-gas shift reactor, WGS. Methane and water produces hydrogen gas and carbon monoxide as shown in reaction equation 1. This reaction helps produce hydrogen, H2, which is needed for ammonia synthesis. Step 3. Synthesis gas compressor. The hydrogen gas produced in the previous step is compressed to the necessary pressure, around 200 to 300 bar, for the next stage in the process. Step 4. Pressure swing adsorption, PSA, hydrogen purification. The hydrogen gas may contain impurities such as carbon, 2, oxide, carbon, 4, oxide, and nitrogen. The PSA system purifies the hydrogen by removing these impurities, leaving high-purity hydrogen for the ammonia synthesis process. Step 5. Ammonia synthesis reactor, reaction equation 2, shows how. Ammonia is produced from nitrogen, sourced from the air, and hydrogen produced from methane. The purified hydrogen gas reacts with nitrogen at high temperature, 400 to 500 degrees Celsius, and high pressure, 200 to 300 bar, in the presence of an iron-based catalyst. Step 6. Ammonia compressor/swatter. The ammonia produced is compressed further to increase its density for easier separation and storage. Step 7. Ammonia condenser/separator. The compressed ammonia gas is cooled in a condenser, where it condenses into a liquid. The separation unit then separates any unreacted gases, which are recycled back into the synthesis process, ensuring a continuous loop. 2.1.1 Transformation of produced ammonia into various commercial fertilizers. Once ammonia is produced via the Haber-Bosch process, it is transformed into various commercial fertilizers through several additional processing and steps. Below is a breakdown of how ammonia is used in the production of fertilizers, which includes the following. 1. Ammonium nitrate fertilizer. Here, ammonia is neutralized with nitric acid, HNO3, to produce ammonium nitrate. As shown in reaction equation 3, through the following production flow. Ammonia gas, NH3, is absorbed in water to form aqueous ammonia. Nitric acid, HNO3, is produced via the Ostwald process, oxidation of ammonia. The aqueous ammonia reacts with concentrated nitric acid to form ammonium nitrate solution. The solution is then concentrated and cooled to produce solid ammonium nitrate crystals. The ammonium nitrate is either granulated or prilled for use as a high nitrogen fertilizer. Uses ammonium nitrate fertilizer. Note that ammonium nitrate is widely used in fertilizers, high in nitrogen, and as an ingredient in explosives. 2. Urea fertilizer. Urea is produced by reacting ammonia with carbon dioxide as shown in reaction equation 4 and 5. Through the following production flow. Ammonia and carbon dioxide react at high pressure, 150 to 250 atm, and high temperature, 180 to 200 degrees Celsius, in a urea reactor. The reaction produces ammonium carbamate, which is then dehydrated to form urea. The liquid urea is then prilled, formed into small pellets, or granulated. Urea is one of the most widely used nitrogen fertilizers, offering a high nitrogen content, 46% N. It's used in agriculture, horticulture, and turf care. 3. Ammonium phosphate. Here, ammonia is reacted with phosphoric acid, H3PO4, to produce ammonium phosphate, as shown in reaction equation 6. Through the following production flow. Phosphoric acid is produced from phosphate rock, treated with sulfuric acid. Ammonia is added to phosphoric acid to form ammonium phosphate. The product is concentrated and then either granulated or prilled. Ammonium phosphate is a key source of both nitrogen and phosphorus, essential for plant growth. It is used extensively in granular fertilizers for crops. 4. Ammonium sulfate. Here, ammonia is reacted with sulfuric acid as shown in reaction equation 7. Through the following production flow. Ammonia reacts with sulfuric acid in a reactor to form ammonium sulfate. The ammonium sulfate solution is then cooled and concentrated. It is either granulated or spray-dried into solid form. Ammonium sulfate fertilizer provides both nitrogen and sulfur, important for certain crops like maize and rice. It is used in agriculture, especially for soils needing sulfur. 5. NPK fertilizers: nitrogen, phosphorus, and potassium. NPK fertilizers are mixed blends of ammonia-based products, urea, ammonium nitrate, ammonium sulfate, with phosphate and potassium compounds. Through the following production flow, ammonia products like urea or ammonium nitrate are blended with phosphate-based fertilizers, such as superphosphate. Potassium, typically potassium chloride or potassium sulfate, is added to the mixture. The blend is then granulated and coated for easy handling and application. Uses of NPK fertilizer. NPK fertilizers are commonly used to provide a balanced nutrient supply for plants, suitable for a wide range of crops. 3.0 Production of petrochemicals. Petrochemicals are chemical products derived from petroleum, crude oil, and natural gas, which are primarily composed of hydrocarbons. They serve as the raw materials for a wide variety of industrial processes and products. Petrochemicals are crucial in producing many everyday goods, including plastics, fertilizers, detergents, synthetic fibers, and fuels. 3.1 Classification of petrochemicals. Petrochemicals are generally classified into three main categories: first, second, and third generation petrochemicals. 3.1.2 First generation petrochemicals. First-generation petrochemicals or basic petrochemicals are the products derived directly from cracking or distillation of crude oil and natural gas. They are often used as feedstocks in the production of more complex chemicals and materials. Examples are alkanes, ethylene, propylene, butadiene, polymers from first-generation petrochemical, etc. 3.1.3 Second-generation petrochemicals. Second-generation petrochemicals or intermediate petrochemicals are primary chemicals that are synthesized from the first-generation petrochemicals. Examples are benzene, styrene phenol, and aniline, methanol, toluene, xylene, synthetic rubber, polymers, etc. 3.1.4 Third-generation petrochemicals. These are consumers or specialized industrial products that are derived from mostly the second-generation petrochemicals and partly the first-generation petrochemicals. Examples are fertilizers, lubricants and greases, cosmetics and detergents, pharmaceuticals, packaging materials. 3.2 Processes of petrochemicals production. The processes involved in production of petrochemicals include 3.2.1 Crude oil refining. The first step in petrochemical production is distillation, where crude oil is separated into different fractions based on boiling points: gasoline, kerosene, diesel, and naphtha. Here's a process flow diagram of crude oil refining. A concise rundown of each main unit in the crude oil refining PFD is as shown below. 1. Desalter. Purpose: remove salts, water, and particulate impurities from incoming crude. How it works: Crude is mixed with wash water and an electric field coalesces water droplets with dissolved salts for separation before downstream corrosion. 2. Furnace, feed preheat. Purpose: raise the temperature of desalted crude to its boiling point range. How it works: crude passes through fired heaters, where it's heated operator 350-380 degrees C before entering the distillation column. 3. Atmospheric distillation column. Purpose: fractionate crude into light and middle distillates at atmospheric pressure. How it works: as heated crude enters the bottom, vapors rise and condense at trays, LPG and naphtha at the top, kerosene and gas oil in middle draws, heavy bottoms exit for further processing. 4. Vacuum distillation column. Purpose: further separate the heavy atmospheric bottoms under reduced pressure to avoid thermal cracking. How it works: vacuum lowers boiling points so heavy fractions yield vacuum gas oil and vacuum residue without excessive cracking. 5. Reformer, catalytic reforming unit. Purpose: upgrade low-octane naphtha into high-octane gasoline components and aromatics, benzene, toluene, xylene. How it works: naphtha mixed with hydrogen passes over a platinum-based catalyst at operator 500 degrees C and 10 to 30 atm. Reactions include dehydrogenation, isomerization, and cyclization. 6. Catalytic cracker, fluid catalytic cracking, FCC. Purpose: crack heavier gas oils into lighter, high-value products, gasoline, diesel, propylene. How it works: under heat, operator 500 degrees C, and a zeolite catalyst, large hydrocarbon molecules crack into smaller ones. Catalyst is continuously regenerated by burning off deposited coke. 7. Hydrotreating unit. Purpose: remove sulfur, nitrogen, and other heteroatoms to meet product specifications and protect downstream catalysts. How it works: distillate streams, gasoline, diesel, jet fuel, react with hydrogen over a sulfide catalyst, operator 300, 400 degrees C, 30 to 100 atm, converting contaminants into H2S and NH3, which are then stripped out. 8. End product separation and storage. After upgrading, each fraction is stabilized, blended, and sent to storage. LPG from light ends. Gasoline from reformer and FCC. Kerosene/jet fuel and diesel from hydrotreating. Residue for asphalt or further conversion. Each of these steps integrates heat recovery, hydrogen management, and recycle loops to maximize yield, energy efficiency, and product quality. 3.2.2 Cracking. Cracking is a key process used to break down large hydrocarbons, from heavier fractions, into lighter, more useful chemicals like ethylene, propylene, and butadiene. This process is typically done using heat or catalysts. 3.2.3 Reforming. Process flow diagram for the reforming process is as shown in this diagram. Reforming in petrochemical production refers to a set of processes used to rearrange or alter the structure of hydrocarbons. It is widely used in refining and petrochemical manufacturing to convert lower-value hydrocarbons, like naphtha, into more valuable products, such as aromatics, olefins, or high-octane gasoline. There are several types of reforming processes, which include catalytic reforming, thermal reforming, and steam reforming, used in hydrogen production. Here's a concise rundown of what's happening in each major step of the reforming train. 1. Preheater. The naphtha feed is first heated to around 500 degrees Fahrenheit, so it's hot enough to drive the downstream reactions. Hydrogen is introduced here, or just downstream, to help suppress coke formation on the catalyst. 2. Reactor section. The heated naphtha/hydrogen mixture passes through a series of fixed-bed reactors packed with reforming catalyst. At roughly 900 degrees Fahrenheit and 300 sig, paraffins and naphthenes are dehydrogenated and isomerized into higher-octane aromatics. The chemical transformations reactions all occur at the reactor section are as shown in reaction equation. The chemical transformations all occur upstream in the catalytic reactor section, for example, A. Dehydrogenation of naphthenes, shown in reaction equation 8. B. Dehydrocyclization of paraffins, shown in reaction equation 9. C. Isomerization of paraffins, shown in reaction equation 10. D. Minor hydrocracking, shown in reaction equation 11. These reactions boost octane by forming aromatics and branched isomers and liberate hydrogen, which is then recycled back to the reactor. 3. Effluent cooler and high-pressure separator. The hot reactor effluent is cooled so that the hydrogen-rich gas and liquid hydrocarbons can be split, typically at 250 sig. The gas, mostly H2, goes off for purification and recycle. The liquid proceeds on for stabilization. 4. Hydrogen purifier and recycle compressor. Any hydrocarbon vapors are scrubbed out of the separated gas, then the clean hydrogen is recompressed and sent back to the reactor inlet. 5. Reforming column, stabilizer. The liquid effluent is fractionated to remove light ends, C4, and any unconverted naphtha boiling below the desired cut. The stabilized tops, now a high-octane Reform 8, are sent on as a gasoline component or petrochemical feed. Every piece of hydrogen not consumed in dehydrogenation is recycled, and the Reform 8 product boasts a much higher octane number thanks to the formation of aromatic rings. 3.2.4 Polymerization. The monomers, such as ethylene, propylene, derived from cracking are then chemically bonded together via polymerization to form polymers, e.g., plastics, synthetic rubber. 3.2.5 Formulation. Formulation in petrochemical production refers to the process of combining various chemical components, often derived from petrochemicals, to create end products with specific characteristics and properties tailored for particular applications. Unlike pure petrochemicals, like ethylene or propylene, which are single compounds, formulation involves blending multiple chemicals to create complex mixtures or products that meet certain performance standards. Key aspects of formulation in petrochemicals are: blending involves mixing petrochemical raw materials, such as solvents, resins, or additives, in precise proportions. Additives, Additives like stabilizers. 4.0 Production of cement. From an industrial chemistry perspective, cement is a finely ground, inorganic powder that, when mixed with water, forms a paste that binds aggregates, such as sand, gravel, or crushed stone, together to form concrete. This binding process is due to the hydration reactions of the cement's constituent compounds, primarily 1. Tricalcium silicate, 2. Dicalcium silicate, 3. Tricalcium aluminate. These compounds react with water to form calcium silicate hydrate, CSH, gel and other hydration products, which provide the binding properties and strength to the concrete. Cement is a critical component in construction, enabling the creation of durable and versatile structures. Here is the process flow diagram for this production. The processes are as described below. 1. Raw materials extraction. Cement production begins with the extraction of raw materials, primarily limestone, CaCO3, clay, sand, and other minerals. These materials are quarried and transported to the cement plant. 2. Crushing and grinding. The raw materials are crushed and ground into a fine powder, known as raw meal, to increase their surface area and facilitate chemical reactions. 3. Mixing and blending. The raw meal is mixed and blended to achieve a uniform composition, ensuring consistent quality of the final product. 4. Preheating and calcination. The raw meal is preheated to about 900 degrees Celsius, driving off moisture and volatile compounds. It then undergoes calcination, where limestone decomposes into calcium oxide, CaO, and carbon dioxide, CO2, as shown in reaction equation 12. 5. Clinker formation. The preheated raw meal enters a rotary kiln, where it is heated to about 1450 degrees Celsius, forming a nodular material called clinker. This process involves 3 complex chemical reactions, including the formation of calcium silicates and aluminates, as shown below. A. Formation of tricalcium silicate or alite as shown in reaction equation 13. B. Formation of dicalcium silicate or bolite as shown in reaction equation 14. C. Formation of tricalcium aluminate as shown in reaction equation 15. These reactions involve the combination of calcium oxide, CaO, with silicon dioxide, CO2, aluminum oxide, Al2O3, and other compounds at high temperatures, around 1450 degrees Celsius, in the rotary kiln, forming the main minerals present in cement clinker. 6. Cooling and storage. The clinker is cooled and stored in silos. 7. Final grinding. The clinker is ground with gypsum, CaSO4, 2H2O, and other additives to produce cement powder. 8. Packaging and distribution. The final product is packaged and distributed to construction sites, ready for use in concrete production. Note that this process involves a combination of physical and chemical transformations, requiring careful control of temperature, composition, and processing conditions to produce high-quality cement. There are several types or classes of cements, including Portland cement, blended cement, specialized cements, masonry cement, hydraulic cement, blended hydraulic cement. These have varied raw materials as feed in the production process but follow the same production route. The varied types cater to various construction needs, environmental conditions, and performance requirements. 5.0 Food Industry, Table Sugar and Table Salt Production. In the food industry, production processes are very wide, with even a particular food having hundreds of methods of production. So, we will deal with process of producing table salt and table sugar that are widely used food ingredients. 5.1 Production of table sugar. Table sugar, also known as sucrose, is a disaccharide carbohydrate composed of glucose and fructose molecules bonded together. Its chemical formula is C2H220. Table sugar is a white, crystalline solid commonly used as a sweetener in food and beverages. The process flow diagram of table sugar production is shown here and also described as follows. A. Harvesting and preparation. 1. Harvest. Cane, fields are cut, mechanically or by hand, and stalks are transported to the mill. Beet, roots are lifted from the ground, topped, washed, and brought to the factory. 2. Cleaning and sizing. Remove dirt, stones, and extraneous plant material. Cane is shredded, beets are sliced into thin cassettes. B. Juice extraction. 1. Diffusion, beet. Cassettes pass through a countercurrent diffuser where hot water leaches sucrose. 2. Milling, cane. Shredded cane is crushed in multiple rollers, releasing sugar-rich juice. C. Juice clarification. 1. Lime and heat treatment. Juice is limed, calcium hydroxide, and heated to precipitate impurities, proteins, coloring matter. 2. Carbonation or phosphatation. CO2, or phosphoric acid plus lime, is bubbled through to form flocks that carry impurities out. 3. Filtration/clarification. Suspended solids, mud, are removed by settling and filtration. D. Evaporation. Clarified juice is passed through multiple effect evaporators, concentrating it to a syrup of 60–65% solids. E. Crystallization, raw sugar. 1. Vacuum pans. Syrup is seeded with fine sugar crystals and boiled under vacuum to supersaturate. 2. Centrifugation. The resulting mask white is spun. Crystals, raw sugar, separate from mother liquor, molasses. 3. Molasses. Mother liquor is either further crystallized to make brown sugar or sold as molasses. The raw sugar produced in section E above is further refined to white table sugar using the 6 steps below. Deaffination. Remelting and raw juice retreatment. Decolorization, using ion exchange resins or activated carbon bed strip. Final evaporation and crystallization. Drying and screening. Packaging and distribution. 5.2 Production of table salt. Table salt, also known as sodium chloride, is a crystalline mineral composed of sodium Na and chlorine Cl ions. Its chemical formula is NaCl. Table salt is commonly used as a seasoning and preservative in food, and it's essential for various bodily functions, such as maintaining fluid balance and nerve function. Commercial table salt is produced at scale by 2 main routes: evaporative processes, from brines or seawater, and mining of rock salt deposits, followed by refining, doping e.g. iodization, anti-caking treatment, and packaging. 5.2.1 Flow descriptions of the production of table salt. The flow description for the production of table salt is as shown in this diagram. The description of this process is as follows. 1. Sources and purification of raw materials. Source: either natural brine/seawater, solar or vacuum evaporated, or mined rock salt. Preparation: brine is screened for solids, rock salt is crushed and, if needed, dissolved to form a concentrated brine. 2. Concentration. Evaporation: brine is evaporated, via sunlight in ponds or by heating under vacuum, until salt solubility is exceeded. Nucleation and growth: crystallization: supersaturated solution forms NaCl crystals, whose size can be controlled by seeding, temperature, and evaporation rate. 3. Solid-liquid separation. Centrifuging/filtering quickly spins or filters out the salt crystals from the remaining mother liquor. Washing and drying. Crystals are rinsed with saturated brine to remove impurities, then dried, e.g. in hot air dryers, to reduce moisture to less than 0.5%. 4. Additives and packaging. Additives: small doses of anti-caking agents, e.g. calcium silicate, keep the salt free-flowing. Iodizing salt, with potassium iodate/iodide, combats iodine deficiency. Packaging: the finished salt is screened to grade, then bagged or boxed for retail, table salt, or bulk for industrial users. 6.0 Petroleum, crude oil, and natural gas upstream production industries. Seismic survey and drilling operations usually precede the crude oil and natural gas production operations. Seismic survey involves carrying out geophysical surveys and mapping subsurface structures so as to identify areas that have commercial amounts of petroleum and natural gas, while drilling operation involves forcing through the subsurface at very high depth to access petroleum and natural gas. Petroleum, or crude oil, is a complex mixture of hydrocarbons and other organic compounds. It's a viscous, dark-colored liquid found beneath the Earth's surface, extracted through drilling. Crude oil is a fossil fuel used as a primary energy source and feedstock for producing various petroleum products. Natural gas is a flammable hydrocarbon gas mixture primarily composed of 70 to 90% methane, 0 to 20% ethane, propane, C3H8, butane, C4H, and other constituents like nitrogen gas, carbon, 4, oxide, hydrogen sulfide, and water vapor. Its composition may vary depending on the source and processing methods. 6.1 Primary separation of produced fluids, petroleum and natural gas. The diagram here shows the process flow diagram of primary separation of well fluids to produced petroleum and pipeline natural gas. The production flow is as described below. Once reservoir fluids arrive at the facility, well pad, flow station or platform, they undergo three-phase separation to separate natural gas, petroleum, and water. The equipment assembled to enhance this separation are as outlined here. A. Inlet equipment and surge knockout. A slug catcher/knockout drum handles intermittent surges, slugs, of liquid and gas. Inlet chokes regulate upstream pressure to optimize separation. B. Three-phase separator. This is the HP separator shown here. A vertical or horizontal vessel operating at an intermediate pressure, e.g. 100 to 300 sig. As the mixture slows down under reduced pressure, gas rises to the top and exits via a vapor outlet. Oil, intermediate density, forms a middle layer, drawn off as stabilized crude. Water, heaviest, sinks and is removed from the bottom. Key internals and controls. Baffles and weirs to minimize re-entrainment. Level controllers to maintain separate interface levels for oil and water. Pressure control valve on the vapor outlet to hold vessel pressure set point. C. Heater treater, if needed. Some separators include a heating coil or steam jackets to break emulsions and improve water-oil split. D. Dehydration/desalting, optional at this stage. Electrostatic desalter. Wash crude with fresh water and apply 5-10 kV to coalesce and drop out residual salts and water. Protects downstream refinery furnaces and catalysts. E. Offtakes and routing. Stabilized crude oil, gas 2 vol% sent to storage or pipeline. Produced water, treated and either re-injected or discharged under environmental permits. Natural gas, transferred to the gas production units. 6.2. Production of natural gas. Utilization of natural gas is compulsory as provided by regulations in most countries that crude oil is produced. So, production of natural gas may be an integrated or a standalone facility in oil-field operations. Stages involved in production of natural gas are outlined as follows. 1. Dehydration. This involved the use of desiccants like alcohols, particularly triethylene glycol, to absorb water from the natural gas stream so as to achieve an amount of water less than or equal to 7 pounds per million standard cubic feet. This is carried out at the cylindrical vertical separated that is shown at the left-hand side of the diagram. Note that some other processes use molecular sieve as dehydrating agent, through the technique of adsorption. 2. Regeneration of desiccants. The dehydrating agents, alcohol or molecular sieves, are not usually thrown away after use. They are rather recycled to puriforms and reused. This operation occurs downstream of the gas dehydration system, although it is not shown in this diagram. 3. Dew pointing. This is the removal of traces of hydrocarbons in the form of liquids from the gas stream. This ensures that the hydrocarbon dew point is less than or equal to -15 C. This could be done using the Joule-Thomson unit or mechanical refrigeration system. 4. Other activities include removal of carbon, 4, oxide and hydrogen sulfide from the gas stream. 7.0. Evaluation of CAPEX, revenue and return on investment of industries discussed here. 7.1. Capital expenditure. CAPEX. CAPEX refers to the funds a company invests in acquiring, upgrading, or maintaining its long-term physical assets such as land, buildings, machinery, process units and infrastructure that will provide benefit over multiple years. In process industries as considered in this study guide, CAPEX covers everything from engineering and equipment purchases to construction, commissioning and startup costs. The CAPEX for medium investments in the selected industries in this resource are as shown in this table. This will enable investor to have an overview of the extent of financial commitments that will be required to start these investments. Resource 7.2 Average revenue generated by medium investment in the selected industries. Revenue is the total income earned by a business or organization from its normal operations, such as sales of goods or services, before deducting expenses. It's a key indicator of a company's financial performance and growth. Revenue can be evaluated using various metrics, including 1. Total revenue, total income from all sources. 2. Revenue growth rate, percentage change in revenue over time. 3. Revenue per unit, revenue generated per unit sold or service provided. 4. Average revenue per user, ARPU, revenue generated per user or customer. 7.3. Return on investment, ROI, from investments in the selected industries. Return on investment is a measure of the efficiency of an investment, expressing the profit earned relative to the amount of capital deployed. It quantifies the percentage return, positive or negative, generated by an investment over a given period. It is calculated using equation 6 as shown here, where net gain equals total revenue, or value, realized, total costs incurred. Total cost of investment equals upfront capital outlay, CAPEX, plus operation expenses, OPEX. In this study, only CAPEX was used. Example: if one invests $1 million to build a production plant, over its first year one earned $300,000 in revenue and incurred $200,000 in operating costs. Net gain equals $1,300,000 to $200,000. $1 million equals $100,000. ROI equals $100,000 / $1 million times 100% equals 10%. General interpretation and deductions of ROI including positive and negative values. ROI greater than 0% means the investment earned more than it spent profitable. ROI less than 0% means the investment lost money. By analyzing these factors, investors will have ideas of which sector of businesses or investment that yield their desired cash inflow. 8.0 Investment strategies for the considered industries. The table here shows the economics of investment for the selected industries in this study. Here we have the average annual revenue for medium investments, their CAPEX, revenue, net profit, return on investment, as well as deduction from the economics of investment. Presenting the data in increasing order of cost of investment, we have the equation as shown in equation 2. Hydrocarbon reforming a table sugar, cement, natural gas a fertilizer, crude oil production, table salt a crude oil distillation. This shows that crude oil distillation into different hydrocarbon substances is the most capital-intensive of these investments, while hydrocarbon reforming is the least. Presenting the data in increasing order of revenue generated, as shown in equation 3, we have cement, natural gas, a fertilizer, crude oil production, table sugar, hydrocarbon reforming a table salt, a crude oil distillation. This shows that crude oil distillation into different hydrocarbon substances generates the most revenue, while investment in cement production generated the least revenue. Presenting the data in increasing order of net profit earned, as shown in equation 4, we have natural gas a fertilizer, cement a crude oil production, table sugar hydrocarbon reforming a table salt a crude oil distillation. This shows that crude oil distillation into different hydrocarbon substances generates the most net profit, while investment in natural gas production generated the least. Presenting the data in increasing order of return on investment, as shown in equation 5, we have natural gas a fertilizer, crude oil production / fertilizer, crude oil distillation, table salt, table sugar, hydrocarbon reforming. This shows that hydrocarbon reforming attracts the highest return on investment, while investment in natural gas production attracted the least. The economic trains of these processes, as shown, inform that an investment with the highest CAPEX may possibly generate the highest revenue, as in the case of crude oil refinery and table salt production in equation 2 and 3. It shows that the net profit earned could also be a function of the amount of CAPEX invested, as seen for crude oil distillation and table salt production, in a similar way to revenue generation, as shown in equation 2 and 4. Also, this in-depth review has shown that investments with least CAPEX attract the highest ROI, as in the case of hydrocarbon reforming and table sugar processes, as shown in equation 2 and 5. This is not to say the investment with the least amount of CAPEX are more lucrative than those with highest amount of CAPEX. This could be investigated by evaluating the capital turnover in the assessment, where capital turnover is a financial metric that measures the efficiency of a company's use of capital in generating sales or revenue, calculated as shown in equation 7. This explains that the accumulated sales in subsequent years of investment, 2, 3, 4, etc., will enhance far higher capital turnover ratio for investment with higher CAPEX, compared to those with lower CAPEX. This is because the total CAPEX for each of the investment compared in the analyses will remain the same. So, emphasize the rule of investments that states, the higher the risk, the higher the reward, a truism. Nevertheless, investment in processes with lower CAPEX give the investors the opportunity to generate revenue and upscale to more lucrative investments with higher CAPEX. Natural gas production in equation 4 and 5 show least net profit as well as ROI. The reason may be due to the fact that natural gas production in this review is considered as a single operation or investment rather than an integrated investment as crude oil and natural gas, since the same source of raw materials, subsurface wells, are required for their investment. So, if the oil and gas facility here is considered as an integrated facility, the net profit will be $165 million annually and a ROI of 89%, making the integrated facility have the same CAPEX as the single value for crude oil production alone, and higher in ROI than the investment in cement and fertilizer productions that were previously higher, when crude oil and natural gas productions were considered as independent investments. Hence, the reason most upstream natural gas investments fail. When producing from solely non-associated gas wells or reservoirs, 9.0 Conclusion and Future Outlook. Industrial raw materials may be viewed to be insignificant and tiny, molecular forms, in their unutilized states. Yet, they are the substances by which strategic processing transform to millions and billions and trillions of dollars. The choice of investment to engage these materials in production could generate revenue, transform the world, and create enormous value. Viewers and learners should continue to follow up with our subsequent videos that will unfold opportunities in other raw materials and their industries, as well as take the available opportunities in the value chains of these industries as well as processes. 10.0 Selected industries in the world that are involved in these productions. A. Cement production. Here are some of the world's largest cement manufacturing groups, with their headquarters and principal production locations. 1. China National Building Material, CNBM. HQ, Beijing, China. Operates the largest network of cement plants across mainland China, with additional joint ventures and expansions in Asia, the Middle East and Africa. 2. Lafarge-Holcim, now Holcim Group. HQ, Rapperswil-Jona, Switzerland. Over 350 cement plants in 70-plus countries across Europe, the Americas, Africa, and Asia. 3. Cemex. HQ, Monterrey, Nuevo Leon, Mexico. Manufactures and distributes cement in more than 50 countries, with major plants in the US, Europe, Latin America, and Asia. 4. Heidelberg Materials, formerly Heidelberg Cement. HQ, Heidelberg, Germany. Runs 130 cement plants in over 50 countries, from Europe and North America through to Southeast Asia and Africa. 5. CRH plc. HQ, Dublin, Ireland. Global operations spanning North America, largest producer of asphalt in the US, Europe, Asia, and the Middle East. 6. Votorantim Cimentos. HQ, São Paulo, Brazil. 50 cement production units in Brazil and plants or terminals in Argentina, the US, Canada, Chile, Peru, Morocco, Tunisia, and Turkey. 7. Dangote Cement. HQ, Lagos, Nigeria. Africa's largest producer, with integrated plants in Nigeria, Abidjan, Ibis, Gboko, plus subsidiaries/terminals in Ghana, Cameroon, Senegal, Tanzania, and Ethiopia. 8. Ultratech Cement. HQ, Mumbai, India. India's biggest cement maker, with an installed capacity of 152.7 TPA, operating 23 integrated plants and 116 grinding units across India. B. Crude oil refining. Here are 10 of the world's leading crude oil refining players, each operating large atmospheric distillation units and where they're based. 1. China Petroleum and Chemical Corp., Sinopec. HQ, Beijing, China. Flagship units, Maoming, Shanghai refineries, each greater than 300 kbd/. 2. China National Petroleum Corp., PetroChina. HQ, Beijing, China. Key refineries, Dushanzi, 240 kbd, Lanzhou, 160 kbd. 3. ExxonMobil Corp. HQ, Irving, Texas, USA. Major distillation trains: Beaumont 609 kbd, Baytown 584 kbd, USA, and Jurong Island 605 kbd, Singapore. 4. Saudi Arabian Oil Co., Saudi Aramco. HQ, Dhahran, Saudi Arabia. Largest refineries: Ras Tanura 550 kbd, KSA, and Port Arthur 630 kbd, Texas, USA. 5. Valero Energy Corp. HQ, San Antonio, Texas, USA. Notable refineries: St. Charles 330 kbd, Louisiana, Port Arthur 340 kbd, Texas, Moreau 185 kbd, Louisiana. 6. Royal Dutch Shell. HQ, The Hague, Netherlands. Key units: Pernis 416 kbd, Rotterdam, NL, and Pulau Bukom 500 kbd, Singapore. 7. BP plc. HQ, London, UK. Major distillation: Rotterdam 400 kbd, NL, and Whiting 430 kbd, Indiana, USA. 8. Marathon Petroleum. HQ, Findlay, Ohio, USA. Flagship facility: Galveston Bay 631 kbd, Texas City, USA. 9. GS Caltex. HQ, Seoul, South Korea. Primary refinery: Yosu 730 kbd, South Korea. 10. Dangote Group. HQ, Lagos, Nigeria. Mega refinery: Lekki 650 kbd. C. Table salt manufacturing. Here are some of the world's leading table salt producers and where their major operations are based. 1. Morton Salt, USA. HQ, Chicago, Illinois. Key plants: Cleveland, OH, Detroit, MI, Kansas City, MO, and Windsor, Ontario, Canada. 2. Cargill Salt, USA. HQ, Minneapolis, Minnesota. Key facilities: Watkins Glen, New York, Alexandria, LA, Anchorage, AK, and St. Clair, MI. 3. Compass Minerals, USA/Canada/UK. HQ, Overland Park, Kansas. Goderich Mine, Ontario, Canada, world's largest underground salt mine. Lyons Mine, Kansas, USA. Winsford Works, Cheshire, United Kingdom. 4. K+S Group, Germany/International. HQ, Kassel, Germany. Vera and Kalawerke Mines, Hesse, Germany. North American Salt, Windsor, Ontario, Canada. 5. Tata Chemicals, India. HQ, Mumbai, India. Mithapur Plant, Gujarat Coast, sea salt evaporation. 6. China National Salt Industry Corp., China Salt. HQ, Beijing, China. Major brine/evaporator sites: Bohaido, Hainan, Tianjin, Danyang, Jiangsu. 7. AkzoNobel, UK Salt. HQ, Middlewich, Cheshire, UK. Middlewich Works, Cheshire brine extraction and purification. 8. Salins Group, France/International. HQ, Rueil-Malmaison, near Paris, France. Key sites: Isle de Rye, Guérande, Ocean Pond Evaporation, L'étang de Berre, Mediterranean. D. Table sugar manufacturing. Here are some of the world's leading table sugar manufacturers and where their main corporate headquarters and flagship production bases are located. 1. Cosan S.A. HQ, São Paulo, Brazil. One of Brazil's largest cane sugar and ethanol producers, with integrated mills across São Paulo state. Zweite Südzucker AG. HQ, Mannheim, Germany. Europe's biggest sugar beet refiner, operating factories in Germany, France, Poland, and beyond. 3. Turios. HQ, Courbevoie, Paris, France. Major beet and cane sugar producer in France, Brazil, India, and West Africa. Vierte Nordzucker AG. HQ, Braunschweig, Germany. Sugar beet processing in Germany, Denmark, Sweden, Czech Republic, and Poland. 5. Mitterfall Group. HQ, Bangkok, Thailand. Asia's top cane sugar producer, with mills in Thailand, China, and Laos. 6. CAPEX International. HQ, Geneva, Switzerland. China's state-owned grain and sugar trader, with refining plants across South America, Europe, Asia. 7. Associated British Foods, AB Sugar. HQ, London, United Kingdom. Cane sugar from Mauritius, Malawi, and South Africa, beet sugar in the UK and Europe. 8. Cargill Incorporated. HQ, Minneapolis, Minnesota, USA. Operates cane sugar refineries in Louisiana, USA, and Ontario, Canada. 9. American Crystal Sugar Company. HQ, Moorhead, Minnesota, USA. One of the largest U.S. beet sugar cooperatives, with factories in Minnesota and North Dakota. 10. Michigan Sugar Company. HQ, Bay City, Michigan, USA. Beet sugar processing in Bay City, Croswell, and Caro, supplying the U.S. Midwest. 11. Raízen. HQ, São Paulo, Brazil. Joint venture of Shell and Cosan, operates some of Brazil's highest capacity cane mills. Ammonia-based fertilizer production. Here are some of the world's leading producers of ammonia-based fertilizers, with their headquarters and flagship production locations. 1. Yara International. HQ, Oslo, Norway. Key ammonia/fertilizer plants. Porsgrunn, Norway, 640 kt NH3/year. Sluiskil, Netherlands, 756 kt NH3/year. Brunsbüttel, Germany, 850 kt NH3/year. Freeport, Texas, USA, 1 metric ton NH3/year JV with CF Industries. 2. CF Industries. HQ, Deerfield, Illinois, USA. Key plants: Donaldsonville, Louisiana, USA, 1.4 metric tons NH3/year. Port Neal, Iowa, USA, 880 kt NH3/year. Lysander, Saskatchewan, Canada, 500 kt NH3/year. 3. Nutrien. HQ, Saskatoon, Saskatchewan, Canada. Key ammonia facilities: Redwater, Alberta, Canada, 1 metric ton NH3/year. Joffre, Alberta, Canada, 700 kt NH3/year. Vanscoy, Saskatchewan, Canada, 420 kt NH3/year. For OCI/NCI, Orascom/CFJV. HQ, Amsterdam, Netherlands. Key plants: Sorfert, Algeria, 500 kt NH3/year. Nat Gasoline, Texas, USA, 1.2 metric tons NH3/year. Bester, Egypt, 300 kt NH3/year. 5. Eurochem. HQ, Zug, Switzerland, operational base in Moscow, Russia. Key plants: Nevinnomysk, Russia, 750 kt NH3/year. Kingisepp, Russia, 500 kt NH3/year. Usalsky, Russia, 500 kt NH3/year. 6. Qatar Fertilizer Company, QAFCO. HQ, Doha, Qatar. Key complex: Ras Laffan Industrial City, Qatar, for metric tons NH3/year via multiple trains. 7. SABIC. HQ, Riyadh, Saudi Arabia. Key facilities: Al Jubail, Saudi Arabia, 1.5 metric tons NH3/year. Yanbu, Saudi Arabia, 600 kt NH3/year. 8. Ma'aden/Alcoa, Ma'aden Phosphate Company. HQ, Riyadh, Saudi Arabia. Key site: Ras Al Khair, Saudi Arabia, 1.05 metric tons NH3/year integrated with phosphate operations. 9. Indian Farmers Fertilizer Cooperative, IFFCO. HQ, New Delhi, India. Key plants: Kulol, Gujarat, India, 370 kt NH3/year. Phulpur, Uttar Pradesh, India, 385 kt NH3/year. Paradeep, Odisha, India, 840 kt NH3/year. 10. Potash Corp, now part of Nutrien. HQ, Saskatoon, Saskatchewan, Canada. Key ammonia site: Colonsay, Saskatchewan, Canada, 190 kt NH3/year. F. Hydrocarbon reforming. Here are some of the world's major refiners operating hydrocarbon, naphtha, reforming units and where they're located. 1. ExxonMobil. Baytown Refinery, Baytown, Texas, USA. 2. BP Products North America. Whiting Refinery, Whiting, Indiana, USA. Rotterdam Refinery, Rotterdam, Netherlands. 3. China Petrochemical Corporation, Sinopec. Maoming Refinery, Maoming, Guangdong, China. 4. Port Harcourt Refining Company, NNPC. Port Harcourt Refineries, Alessa Ilim, Rivers State, Nigeria. 5. Marathon Petroleum. Garyville Refinery, Garyville, Louisiana, USA. 6. Valero Energy. Port Arthur Refinery, Port Arthur, Texas, USA. 7. Chevron, Pasadena Refining System. Pasadena Refinery, Pasadena, Texas, USA. 8. Dangote Group. Dangote Refinery, CCR Unit, Lekki Free Zone, Lagos, Nigeria. G. Crude oil and natural gas production. Here are some of the world's leading companies active in both crude oil and natural gas production, with their headquarters and principal upstream regions. 1. Saudi Arabian Oil Company, Saudi Aramco. HQ, Dhahran, Saudi Arabia. Key production, Ghawar, Safaniya and Manifa oil fields, master gas system, extensive onshore gas network. 2. Gazprom. HQ, Moscow, Russia. Key production, West Siberian gas fields, e.g. Urengoy, Yamburg, oil via Gazprom Neft subsidiary. 3. Exxon Mobil Corporation. HQ, Irving, Texas, USA. Key production, Permian Basin, Gulf of Mexico, Bakken and Appalachia, USA, offshore Guyana, Stabroek. 4. Royal Dutch Shell plc. HQ, London, United Kingdom. Key production, North Sea, UK/NL, Gulf of Mexico, Nigeria, Malaysia. 5. BP plc. HQ, London, United Kingdom. Key production, North Sea, Gulf of Mexico, Alaska, Azerbaijan, Egypt, Trinidad and Tobago. 6. Chevron Corporation. HQ, San Ramon, California, USA. Key production, Permian Basin, Gulf of Mexico, California, Colorado, New Mexico, West Africa. 7. TotalEnergies SE. HQ, Paris, France. Key production, deep offshore, West Africa, North Sea, Brazil's pre-salt, LNG, Qatar, Yemen, U.S. Gulf of Mexico. 8. PetroChina Company, Ltd. HQ, Beijing, China. Key production, Daqing and Chongqing onshore oil and gas fields, Darim and Sichuan basins. 9. Petróleo Brasileiro S.A., Petrobras. HQ, Rio de Janeiro, Brazil. Key production, offshore pre-salt fields, Lula/Tupi, Búzios, and Campos Basin. 10. ENISPA. HQ, Rome, Italy. Key production, North Africa, Libya, Egypt, Kazakhstan, Congo, West Africa deep offshore.